Hi everybody. Today we look at Maxwell's equations. Now, before Maxwell came into the scene, the equations governing electrodynamics were del dot E equal to rho by epsilon 0 that we obtained from Gauss's law, del dot B equal to 0. No special name for that law. Del cross E equal to minus dou B by dou T for the Faraday's law. Del cross B equal to mu 0 J for the Ampere's law. So these were the four laws in electrodynamics before Maxwell. Okay. Now, if you take equation 3. If you are taking equation 3 where del cross E is equal to minus dou B by dou T, and if you take the divergence, that is del cross E, that will be equal to del dot minus dou B by dou T. I can take this del dot inside this differential or the partial derivative. So minus dou by dou T of del dot B. Del dot B is 0 by the second rule. So we get 0 on the right hand side. Left hand side is 0 because the divergence of curl is equal to 0. Okay. So this is from equation 3. And we have equation 4. Suppose we take the divergence of this. Then we have del dot del cross B as equal to mu 0 del dot J. Okay. If we are taking divergence for equation 4, we have this del dot del cross B as equal to mu 0 del dot J. Left hand side is 0. Okay, because we are taking divergence of curl of a vector, so left hand side is definitely 0. But on the right hand side, we have this del dot J that is equal to minus dou rho by dou T. Okay, the rho is the charge density, and this is 0. Del dot J is 0 only for steady currents. Okay, it is 0 only for steady currents. So in general, the right hand side here, this is not equal to 0. So left hand side is definitely 0, but right hand side is not 0. So a problem is there. Maxwell fixed this problem. For that, what he did was he knows del dot J equal to minus dou rho by dou T, and for rho he substitutes from equation 1. Equation 1 says del dot T is equal to rho by epsilon 0. So he substituted for rho as del epsilon 0 del dot T. So minus dou by dou T epsilon 0 del dot T, which is minus del dot epsilon 0 dou E by dou T. Okay, I can take del outside. So minus del dot epsilon 0 dou E by dou T. Okay, so del dot J is equal to minus del dot epsilon 0 dou E by dou T. Suppose, so we have this in our mind. Suppose equation 4 we modify. Actually, Maxwell modified equation 4, which is del cross B equal to mu 0 J as this. Del cross B equal to mu 0 J plus mu 0 epsilon 0 dou E by dou T. Okay, suppose we are writing that equation 4 like this. And now if I take the divergence del dot del cross B, that will be equal to mu 0 del dot J plus mu 0 epsilon 0 dou E by dou T. Okay, and del dot J we know del dot J is dou rho by dou T, which is equal to minus del dot epsilon 0 dou E by dou T. So here I can write dou rho by dou t, and this thing is this thing the dou by dou t of del dot t. Okay, dou by dou t of del dot t, or epsilon 0 dou by dou t of del dot t, that is equal to dou rho by dou t. Okay, that this is actually dou rho by dou t. So we have this minus mu 0 dou rho by dou t here, then mu 0 dou rho by dou t, that is equal to 0. So left hand side is 0, right hand side is also 0. Okay, left hand side is 0, right hand side also 0. So this problem with this equation is solved. So we are modifying, or Maxwell modified equation for like this by introducing a term, an additional term mu 0 epsilon 0 dou E by dou t, so that if you take del dot del cross B, you get 0. Okay, and this equation also adds to the aesthetic appeal, because we have this equation del cross E equal to minus dou B by dou t, which is the Faraday's law, which says a change in magnetic field will induces an electric field. Okay, that is what Faraday's law is telling us. If we add this additional term here to the Ampere's law, this equation has this dou E by dou t, which says the change in electric field induces a magnetic field. Okay, change in electric field induces a magnetic field. Okay, so Maxwell added this term, and he called this extra term as displacement current, JD, that is equal to epsilon 0 dou E by dou t, because it is adding to the current density. Okay, so in this equation, we are adding this. If you take mu 0 as common factor, we have J plus epsilon 0 dou E by dou t. Okay, so here we have current density, and here the corresponding term is epsilon 0 dou E by dou t. So this is the displacement. This is called displacement current density. Okay, because J is current density. Okay, so the displacement current JD is equal to epsilon 0 dou E by dou t. So we have the Maxwell's equations now. Del dot E rho by epsilon 0, del dot B 0, del cross E minus dou B by dou t. So no change up to this third equation. The fourth equation, a term is added, an extra term is added by Maxwell, which is epsilon 0 dou E by dou t. Okay, so mu 0 J plus mu 0 epsilon 0 dou E by dou t, which is the Maxwell's corrected term, which makes del dot del cross B exactly equal to 0. Okay, on the right hand side. Then we have the Lorentz force law, which is F equal to QE plus QV cross B. Okay, the force experienced by a charge in a combined electric and magnetic field, that is there. So F equal to QE plus QV cross B. So these 5 equations, these 4 Maxwell's equations with the corrected fourth equation, and then the fifth equation, F equal to QE plus QV cross B. These 5 equations summarizes the entire theoretical content of the classical electrodynamics. Okay, so these 5 equations summarizes the entire theoretical content of the classical electrodynamics. In fact, the equation of continuity, which is del dot J equal to minus dou rho by dou t, this can be derived from equation 4. Okay, this can be obtained from equation 4. You take del dot del cross B, that is taken here, the left hand side is 0, and from here we get del dot J plus this term is dou rho by dou t, so del dot J equal to minus dou rho by dou t. So the classical electrodynamics, theoretical content of the classical electrodynamics is completely represented by this these four Maxwell equations along with this Lorentz force or the force